Hi everyone, welcome to the Abaqus tutorial. Before we get going, I'll just give you a quick introduction on why we picked Abaqus and not any other finite element software. So basically, it has very broad features. It's very general, so you can do different type of analysis on it. There's also a student version available with the one you're running right now, and the documentation is pretty good. So let's get going here. This is the screen you're going to get when you launch the software. You might have a different version here, but you should still find this button with standard and explicit model. So we'll just go with this. And then today, to go over the software, I'm just going to run 3 examples and some variation of these examples. So I go through all the steps to create these examples, and at the same time, this will allow us to see some tips and tricks you can use when you use finite element softwares, and this will also connect to the theory we've been seeing with Reza in the course lately. All right, so let's go right in and look at our first example. First, we're going to do a plate with a hole and try to figure out the stress concentration factor in the finite element and see if we can recover the theory. So let's go back in Abaqus, and you'll see in Abaqus there's many different ways to achieve the same thing, and here you'll see that's what we call the tree on the left, and these are all the components you'll be want to create or that are necessary for your analysis. You're probably not going to use all of them, but really most of the analysis will always require you to create the part. So this will include all creating the part geometry, but also the mesh. You'll need to define a material. You'll also need to create the analysis type. Let's say if you do a dynamic analysis or an eigenvalue frequency analysis or a static analysis. Today we're just going to focus on general static analysis. And you'll also need to define the loads and the boundary conditions. And in Abaqus, if you want to create a part or a material, it's pretty easy here. You can simply double click and then you'll get the dialog of create part here. You also have all these buttons here that are sort of associated with some of the actions you can do in the tree. So if we look at this button here, it's actually a create part button, and it will lead me to the exact same dialog. And then if we look at the way we would want to create a material, you can double click material and then it will lead you to the edit material dialog. But you can also go from the buttons here just by the viewport. Here you'll notice that the buttons have changed. That's because we changed module when I double clicked on material, and you can navigate through all the modules with this menu here. So if I go back in the part module, then we recover the old buttons, and then I'll go back to the property model for material. You can use one or the other. You'll have a few more options with these buttons here. And even some of these buttons will have an equivalent in the menu bars here, as I could also create a material from here, like material create, same thing again. All right, so let's create that part. So I'm gonna go with my favorite option here is just to double click on the part, and I'll name it plate, be very original. And then here in the modeling space, first, for this one, we're going to go 2D because it's just a plate. It's a 2D structure. Deformable because we want to assess the strain and the stress on this plate. And here, base feature, it allows me to just pick how I'm going to create the part. Here in 2D, my base feature could be a shell. I'll be defining my part as if I was seeing it from the top. Approximate size, let's say our plate is going to be 100 long, 24 wide. So I'll just say here 150 so we make sure we can see it. Some of you will notice that there's no unit here that is defined. I'm just defining a number. That's actually how Abaqus works. You won't find any units in Abaqus, and it's rather based on what we call unit consistency. So here I have this web page. that explains a bit what unit consistency is. And Abaqus will expect you to input units and values that are coherent with each other. So here, if I decide that 150 is in meters, I'll need to use kilos, seconds, and Newton. If you maintain the right scale for each of them, you'll obtain the right answer. Like let's say if we do divide newtons per meter square, we would obtain pascals. Another one that I really like is this one. That is more useful for mechanical engineering applications as you're using the millimeter scale here. And just to show you the example again, if you divide newtons per millimeter squared, you'll obtain MPAs. So that's why we say it's consistent. So for today, we're going to use this one, the one with millimeters and newtons. So we'll go back in here. We're talking about 150 millimeters now. So I'll continue, and then I'll get into a new toolbox here, or like a new module, which is the sketching module, where I can create my part. So I'll put the hole in the middle, and if I want my plate to be 100 long, I'll use this guy here to create a square. You just type in the coordinates. So minus 50 and minus 12. Press enter. So now it has picked the corner for me. So I'll do the same thing on the other side. So now I'm at 50, 12. So I got this square created. So if you click down the wheel, it basically means accept or confirm next. So while I'm here, if I click the mouse button, the middle mouse button, or button 3, then it accepts. So then I just moved out of the tool. I just got away from the tool. And then if I click the mouse button again, it would be equivalent as clicking done here. So I'm going to click the button 3, and I get my part. I need a hole in this part, so I'll create a new sketch on top of the part. To do this, I'll use the extrude button, and I just click on it, and then it brings me back again in this sketching module, and I'll use circle. Fairly simple here. I'll just pick the center, and let's make this hole with a radius of 3. So I'll just go here and put 3, 0. So now I got my hole. I click on button 3, then I just got away from the tool, click again to confirm, and now I got my part. So now that I got my part, I'll need to mesh it. So in the tree, you'll see now that I created a part, there's a little plus that appeared next to the part because it's containing all the part I would create. But for now, we're just creating one. And then I can expand again, and we see that this part has a bunch of features. And one of them is the mesh. So I'll double click the mesh button and access the mesh module where I can start meshing. In Abaqus, the way the mesh is created from a user input seed. So I'll need to put a seed on my part to give an idea about what size I want the mesh to be. So I can create a general seed like over the whole part, and let's say that was 100 long, and we want 50 elements along the length. The approximate element will be 2 millimeters wide. So I press apply, and then I see these seed nodes appear all over, like on every edges. So I click OK. And then here with this button, I can also see my seeds. And then since we're going to be interested in the stress around the hole, I can create a local seed that Abaqus calls like just seed edges, and come and pick the edge here, and then button 3 again. And then I can make this somewhat finer. So let's make this, let's say 4 times finer, and I'm going to say 0.5 instead, and then press apply. Okay, and now we see that there's way more seeds around the hole. Next, I'll just press on the mesh part button. OK to mesh part, yes. And then here we go, I got my mesh, and you can clearly see that I got what I wanted with the finer mesh around the hole. Now the mesh has been defined. I need to define the element type. So I'll use this here, this other button that is the assign element type. Click on it. And then here I have a few options, but really like there's not so many that are useful for us. I'd say like here we would hesitate between plane strain or plane stress. And here this problem is a thin plate. We haven't defined a thickness yet. Let's say it's going to be 1 millimeter thick. So clearly it's a plane stress situation. Here, the geometric order, we're going to explore this later with some other problems, but we're going to keep it linear. So that means there's only one node per corner on these elements. If I was to pick quadratic, there would be also a node in the middle of each edge on these elements. And then reduce integration, we're going to keep it reduced, and then it's going to be covered later in the course what it means to do full or reduced integration. All these features picked together will lead to an element code. So right now we're using CPS4R. And just to show you how it would change if I was using the quad elements, here it would go to S8R because it becomes an 8-noded element, while here it's a 4-noded. R is for reduced integration. The S here is for plane stress. If I use plane strain, I got plane, and E stands for strain. So really like this code has a meaning. The part definition here is not yet quite complete. The part doesn't really know what it's made of yet, but we haven't defined any material. So that's what we're going to do next, and we're going to come back to the part later. So I'll just reduce that in the tree and then go and create the material. So I'll double click on the material here, and then I can give it any name. So here you're going to give your material a name just for reference when you're going to assign it to your part, or more precisely to your section. So really you can use anything you want. So I'll just use something for the nerds out there, and because anyway none of what we're doing here is real, so let's just use fake materials. And then here in the materials you can use well, you can define tons of different properties for it, but really we don't need all of them. Like we don't need to define thermal conductivity or anything. We're just going to be defining the elastic properties. So you go in mechanical and elastic, and then it lets you input just the classical way of defining a material. It's Young's modulus and Poisson's ratio. If you remember with the unit consistency we were looking at, we're using megapascals. And let's say imagine that Beskar is somewhat stiffer than real steel. We're going to say it's 250 GPa. So that means 250,000 megapascals. And then it has, let's say, a Poisson's ratio of 0.25. And that's it. Defining the materials is pretty easy when we do linear elastic analysis. From here, I cannot define the material directly to the part. In Abaqus, I need to do this through a section. So I'm going to create a section here by double clicking. Here, I have to define my section, and then you really need to pay attention here, as some people may think that I would use a shell category because this is like a thin part. I'm actually using homogeneous solid, and that's because I'm in the 2D plane. We'll see later when we do some beam analysis what it means to use shell and the beams. Here, although it doesn't seem intuitive, we're going to use the solid homogeneous section. And then again, here the name is just for reference. So I'll call it like this, Beskar section, and continue. So then the section now wants to know what it's made of. And then the only material we created so far was the Beskar, so we're stuck with it. And that's actually here that you're going to define the thickness of your part. So I just have to activate this, and now I said that the plate was a millimeter thick. So that's what it means, and then I press OK. So now I got my material and my section created. I'll go back to the part and do the section assignment. So I double click on it again, select the regions to be assigned a section. So here, like you'll find that just underneath the viewport, you'll always have like pretty useful prompts. So I'll just click on the part. I don't necessarily want to create a set here. So I'll just unclick this. So now I select the whole part, click done, and assign the section. So again, like that's the only section we have access to. And the thickness will come from the section, because I just defined it there. Thickness is assigned from the section, click OK. Now you see the color changed here. That means that the part now has a section assigned to it. So I would say we're halfway done here. As I said earlier, we have like four big steps we need to do. The part and geometry, materials and section here, the analysis type, and boundary conditions and load. So now we're gonna go for the third step, which is the step and the analysis type, which is fairly easy one, and then just double click on the step. And here you have a bunch of options that are not very of interest for us here, and we're gonna pick just a static general. So I'll call this static, or static stress concentration. Here it's asking me how I want this step to be solved, and well, this is good. We won't undergo large deformations. Keep this off. Time period is like the time period this is undergoing is not very relevant, so we'll just keep 1. And then here with the incrementation, it's not very important here right now because it's just going to be solved in one shot. So I'll click OK, and now my step has appeared here. Next, a thing I haven't mentioned yet is the assembly module here. So really, when you create parts in the part module, it's like filling a library with parts. But right now, it may seem a bit weird because we're doing our analysis on only a single part. So it feels weird to just import that single part that is just the center of interest of our analysis into the assembly where it stands alone. But I mean, that's how Abaqus is set up. I need to double click instances, and then instances will allow me to bring in the plate. So then create instance from part and click OK. So now it has changed color to a darker blue, and really the darker blue is the signature of the assembly module. So when you see dark blue, that means you're in the assembly module, and that's actually where you're gonna be defining the loads and the boundary condition. So now we're going to our last step, which is defining load and boundary conditions. I'll start with the boundary conditions. I'll just fix the plate on one side. So double click on boundary conditions, and it's an initial boundary condition. So I'll define it in the initial step, and I'll call this one fix. And I'll fix the left side, mechanical displacement rotation, continue. And then I get prompted select regions for the boundary conditions. So I click the edge, click done, and I don't want it to move along the, I'll say, the X and Y directions. And then rotations around Z is not very relevant here. If I would click it, Abaqus would just sort of ignore it. Now this is clicked, I'm gonna do the same thing on the other side. I'm gonna create a force, so not quite the same thing. So I'll double click on the load. The load has to be created during the loading step, and then this is gonna be let's use pressure load, so it relates to the stress more easily. So we'll call this pull continue. I'll select the edge here, done, and magnitude, let's say 500 megapascals. Okay, so now it's pushing in. Okay, so I don't like, yeah, because obviously it's a pressure load, so it's pushing on the surface, but I want it to be pulling. So I'll just go on there, double click on the condition, or like on the load I just created, and invert it. That's just putting the minus sign there. Okay. And now I see my arrows are pointing out, so I'm going to be pulling on the plate. So now my model is complete. I'll need to submit it for analysis. To do so, I'm going to go create a job. So again, double click. It wants to know the job name, but you know what? First, I'll just change the model name, because then we're going to be creating more models afterward. I'm just going to go here, rename this, and I'm going to call this full plate. Okay, and let's go there again, and then I'll just call the job the same name, full plate. Press continue, and then here I have some options for computation. So if I want to assign more memory or more cores to solve it faster, but I'll tell you this is a very small problem, so I don't need to care about this at all. So I'll just press OK here. And just to organize our work a bit better here, I'll change the work directory so everything happens in the convenient directory for me. So I'll just go here, set work directory. So that's just like my standard work directory where I do all my analysis, but I'll just go in there and create an extra directory, and we'll call it tutorial. Okay, and then click on it. Okay. So now I'll be solving everything in there. So I press OK, and then I go here, and then here you have a few options. When you're really confident about what you're doing, you can directly submit your job, but you can also do a data check, so that will let you know if you forgot something. So let's just do it. Check completed successfully. Great, I didn't make any mistakes. That's reassuring. And then I'll just continue. The analysis is complete. First, I'll go show you what it looks like in the folders. So I'll just open what we created here in the tutorial folder. So it created a bunch of files that are all named with our job name. And I would like to draw your attention to first the input file, because this file was created first. Because that's not something I haven't mentioned yet, but really the way finite element software works, they will use your inputs and whatever you create in the user interface and write a text file that is then readable and executed by the solver. So I'm going to show you how it looks like, opening the input file with Notepad++ here. Like everything's in there. Like you'll see the first part is the coordinate of every node, and then so it goes on, and then after that it's associated the node numbers with which each element. So this is going to be the element number and then the three nodes connected to it. So it goes on for a while, and at the very end you'll be defining like the material. So here you see we recover what we just created earlier, the material, the type of step, which is a static step, the loads, so we see here the pressure I defined earlier, and then here are just like the output requests, so we can see something at the end. So in the end, we could imagine that the Abaqus interface here is only useful to write a text file. So you do all this and it just all goes to a text file, and that's what the Abaqus core or the solver is going to use to compute. So now let's look at the results and jump in the post-processing part. So really the third part I was talking about, pre-processing, what we all did, the solving that basically took a second, and then we go into the post-processing. So you just right click on your job and check the results. So here we're interested by the stress on the side of the hole. And to do so, I'm just going to use the deform shape button. Now I can see some stress. Here we have some more viewing options, and I can ask to see the the maximum. So I'll ask to see location for maximum stress. As expected, it's by the side of the hole. And we see here 1.327 gigapascal. Let's see how it relates to the website and see if we manage to recover the theory. Back to the website here where we could calculate the stress concentration, we know that we define the width as 24 and the diameter as 6. So it tells me the stress concentration should be 2.42. To find the max stress, I need to use the KT we just found times the nominal stress. But the nominal stress is not quite the one we applied there on the edge. To find the force, we'll use the nominal pressure we're applying times the bulk width divided by the local width. It's 18 because it's 24 minus 6. So that's what we get, 666. So that's the stress. If there was no stress concentration there like that, because the section is smaller. And then we will multiply this by the stress concentration factor times 2.42. And then we obtain 1613. All right, so what we see here is like it's not quite a good match, eh? Like we got 1.3 while we just found 1.6 gigapascal. So next we're gonna refine the mesh, like overly refine it to see if it helps.
5 minutes later.
So for the sake of time, I just went in and remeshed the part. We see what you can see with a much finer mesh, and you see that the result is somewhat converging towards our result of 1.6 gigapascal. Now we're at 1.5. I'll show you a way to obtain the same result in a much more efficient way, taking advantage of the symmetries. So I'll create a new model, but I'll just go way faster this time. I'll just take a bit more, like I'll take my time on the details that are new, but we'll be doing some stuff over again. So we'll just go back to the model and create a new model. So we know that the big stress concentration is on this edge here, and especially around the hole. So we're gonna come in and mesh this edge and use what we call the bias. So a single bias will make the mesh size more dense on one side and just spread out on the other. I'll just apply it. I want to see how it's being defined right now. Okay, so right now it's way too fine. Just make this a bit coarser, and you see that it's fine on the outer edge. It's not what I want, so I'll flip it. So now I got a very fine mesh around here that is around 0.1, so it's 5 times finer than what we had earlier, and we want a very good result. So let's just push it and use this 0.05. So it's going to be very fine around here. And then I click OK. I'm going to do the same thing on this edge and define it very fine around the hole. I click Done. And let's say I apply the same thing. Again, we see we have like a very fine mesh. We're going to get a very fine mesh around this here. And then I know my other coordinate is 0.5. So let's just use this 0.5 and spread it out with a more coarser bias towards the bulk side of the plate. So here I'm happy with this, and then I'll do the same job here with the edge seed, and the minimum size will be 0.5, and let's allow it to go up to 3. Flip again, so the finer side is here, perfect. Okay, and I'll do the same thing here, and done. 0.5 and 3. And now this one's the right direction. So I click OK. And let's mesh this part, see how it looks. All right, very nice. Like we should expect to have like very nice stress definition around the stress concentration area. We'll just make sure we're defining the right element here: standard, plane stress, linear, reduced integration. Okay. And then what's really different here, because we're only using a quarter of the plate, is the symmetry boundary condition. So here I'll go back to initial, and call this one symmetry X. And the type of the symmetry boundary condition is going to be symmetry. How surprising. And then click continue, select the edge, done. And then I'm going to assign X symmetry. So that means that the x-axis is coming out of the symmetry plane. And then we see the x-axis is going from left to right. So click OK. I'm going to do the same thing again with the bottom edge, or it's more like the middle edge. And I'll call this one symmetry Y. In the initial step, selecting the edge, and Y sim. And that's it. My symmetries are defined. And that's all I need. I'll create my job that is now called quarter plate. Standard is good here, and submit. So the analysis is completed. Let's look at the results, see if we're getting closer to the final results. And we look at the stress. And again, we're sort of getting close, but it looks like we would need an even finer mesh to get in the 1600 here. So I'll just do it quick, see if it helps.
Moments later.
So here we go. I made the mesh 5 times finer around the hole. And if we zoom in, because now it's just, we can't see much, we can see that we're actually getting closer to the result we're expecting. Okay, so that was it for plates and stress concentration.